Representation learning sits at the core of almost every modern AI system deployed in production today. When teams talk about language models, recommendation systems, or search engines, they are fundamentally talking about how data is represented internally. In real-world AI organizations, strong representation learning capability often separates teams that can scale models effectively from those that struggle with brittle pipelines. Many early AI professionals assume embeddings are just a pre-processing trick, but in practice, they define how information flows through entire systems. Poor representations lead to downstream failures, misaligned models, and high maintenance costs. As your career progresses, the ability to reason about representation quality becomes a hiring signal for senior and staff level roles. Understanding embeddings is not optional if you want to work on systems that generalize well, transfer across tasks, and remain stable in production environments. This lesson focuses on building a practical and career relevant understanding of representation learning. In industry AI teams, engineers are rarely judged on whether they know a specific paper, but on whether they understand how embeddings behave under real constraints. These objectives reflect skills used daily in search, ranking, and recommendation systems. A common mistake is treating these topics as theoretical only, which limits your ability to debug or improve deployed models. Professionals who understand these objectives can make better design trade-offs and communicate effectively with research and platform teams. From a career perspective, this knowledge directly impacts your ability to move into senior engineering, applied scientist, or machine learning architect roles. Weak understanding here often results in stalled career growth when systems become more complex. A good representation captures meaning in a way that downstream models can use reliably. In production AI teams, representation quality directly impacts model performance, latency, and retraining frequency. Engineers often believe more dimensions automatically mean better embeddings, but this usually increases noise and cost. Poor representations force teams to compensate with complex models, leading to fragile systems and burnout during maintenance cycles. Strong representations reduce engineering overhead and simplify experimentation. From a career standpoint, professionals who understand representation trade-offs are trusted with core system components, while others remain limited to peripheral tasks. This distinction affects both responsibility and long-term growth within AI organizations. Early NLP systems relied on one-hot encodings that carried no semantic structure. Dense word embeddings changed this by encoding meaning through usage patterns. In real AI products, this shift enabled scalable language understanding without manual feature engineering. A frequent misconception is that word embeddings alone solve language understanding, which ignores context and polysemy. Teams that over-rely on static embeddings often face accuracy ceilings. Understanding this transition helps professionals recognize why modern systems move beyond static representations. Career-wise, engineers who grasp these historical limitations are better prepared to evaluate new architectures instead of chasing tools blindly. Contextual embeddings marked a major shift in representation learning by allowing meaning to change based on usage. In production NLP systems, this dramatically improved accuracy for tasks like search and intent detection. Many professionals mistakenly treat contextual models as drop-in replacements without considering cost and latency. This often leads to over-engineered systems that fail performance budgets. Understanding when contextual embeddings are necessary is a key architectural skill. From a career perspective, this judgment separates practitioners who design sustainable systems from those who optimize only for benchmarks. Self-supervised learning allows models to learn structure without manual labels. In industry, this paradigm enables teams to leverage massive data sets that would otherwise be unusable. A common misunderstanding is that self-supervised learning removes the need for supervision entirely, which leads to poor evaluation practices. Effective teams combine self-supervised pre-training with targeted fine-tuning. Professionals who understand this balance are better positioned to lead large-scale model initiatives. Misapplying this paradigm often results in wasted compute budgets and slow iteration cycles, impacting both project success and professional credibility. Contrastive learning trains embeddings by comparing examples rather than predicting labels. In real AI teams, this framework underpins many state-of-the-art representation models. A frequent career mistake is treating contrastive loss functions as interchangeable, ignoring their geometric implications. Poorly designed contrastive setups lead to collapsed or biased embeddings. Engineers who understand alignment and uniformity can diagnose these failures early. This expertise reduces costly retraining cycles and positions you as a trusted contributor in representation-heavy systems. SimCLR demonstrated that strong representations can be learned with simple architectures and large-scale contrastive training. In production environments, however, its resource requirements must be carefully managed. Many teams attempt to replicate research results without accounting for infrastructure constraints, leading to stalled projects. Understanding the trade-offs between performance and cost is critical. Professionals who can adapt these methods pragmatically gain influence in system design decisions. Misalignment here often leads to burnout and reduced trust from stakeholders. Metric learning focuses on structuring embedding spaces using explicit distance constraints. In applied AI roles, this is common in face recognition, product matching, and retrieval systems. A common mistake is ignoring sampling strategy, which leads to slow or unstable training. Engineers who understand hard negative mining can dramatically improve convergence. From a career standpoint, this knowledge signals readiness for complex similarity-based systems and increases responsibility in high-impact projects. Dimensionality reduction methods like t-SNE and UMAP are diagnostic tools rather than modeling solutions. In real AI teams, they are used to understand embedding behavior and failure modes. A frequent misconception is using these visualizations as evidence of model quality. Misinterpretation leads to false confidence and poor decisions. Professionals who treat these tools correctly can identify dataset issues early. This skill improves system reliability and enhances your reputation as a careful and methodical practitioner. Knowledge distillation allows teams to transfer embedding quality from large models to smaller ones. In production systems, this is critical for meeting latency and cost constraints. Many professionals underestimate the complexity of distilling representations rather than predictions. Poor distillation leads to silent performance degradation. Understanding this process enables engineers to deploy scalable systems without sacrificing quality. Career-wise, this expertise aligns with senior-level ownership of production pipelines. Evaluating embeddings requires more than accuracy metrics. In industry, embedding failures often surface indirectly through downstream degradation. A common mistake is relying solely on offline benchmarks. Effective teams combine intrinsic tests with production monitoring. Professionals who understand evaluation nuances prevent costly regressions. This capability is a strong signal for technical leadership roles and reduces long-term maintenance burden. Embedding-based retrieval underpins modern search and recommendation systems. In real-world deployments, performance depends as much on indexing and infrastructure as on model quality. A common misconception is that better embeddings alone fix retrieval issues. Engineers who ignore system-level considerations struggle to deliver results. Understanding this interaction improves system outcomes and positions you for end-to-end ownership roles. Efficiency techniques make embedding systems viable at scale. In production AI teams, quantization is often the difference between a prototype and a shipped feature. Many professionals avoid this topic, viewing it as low-level optimization. This limits their impact on real systems. Engineers who understand efficiency constraints gain credibility with platform and infrastructure teams. This skill directly affects career progression in applied AI roles. Representation learning is not an isolated research topic, but a foundational skill for applied AI careers. In industry, embeddings influence system scalability, reliability, and cost. Professionals who misunderstand this often plateau early, limited to narrow implementation tasks. Mastery of embedding geometry, training paradigms, and evaluation practices enables broader ownership and leadership. This lesson provides a framework for thinking critically about representations rather than memorizing techniques. As AI systems grow more complex, this depth of understanding becomes a long-term career advantage rather than a short-term optimization.